From lunar orbit, a total solar eclipse can last almost 1 full hour. That is what a crew of astronauts recently experienced during a flyby of the moon. And they brought back an extraordinary set of images that show the moon, the sun, and the Earth from a perspective humans have never had before. These photographs are not just beautiful, they also give a very clear look at how eclipses work in space, how the lunar surface is shaped by billions of years of impacts, and how fragile our planet looks from hundreds of thousands of kilometers away. To understand what we are seeing in these images, it helps to start with the journey itself. The crew traveled aboard the Orion spacecraft as part of the Artemis 2 mission, a major step in returning humans to the vicinity of the moon. Their path took them past the moon at a distance of about 4,000 miles above the surface. That might sound close, but at that altitude, the moon still fills a huge fraction of the sky outside their windows. During this trajectory, the spacecraft briefly broke a long-standing record. For a short time, these astronauts became the most distant humans from Earth in history, surpassing the record set in the late 1960s by the Apollo 8 mission. From that distance, Earth shrinks into a small, bright globe, easily hidden behind the curve of the moon. Some of the first images show Orion approaching the moon, with our planet visible as a tiny disk in the background. In a few frames, you can see 3 worlds at once: the gray, cratered moon dominating the foreground, the spacecraft itself, if the camera is pointed just right, and far away, the blue and white Earth. It is an instant reminder of the scales involved. The moon is about 1/4 the diameter of Earth, yet from close range, it can completely hide our planet from view. The most striking sequence of images captures a total solar eclipse as seen from lunar orbit. On Earth, a total solar eclipse happens when the moon passes directly between the Earth and the sun and casts a narrow shadow on Earth's surface. In this case, the situation is reversed. The spacecraft passed behind the moon as seen from the sun, so that the moon blocked the sun from the astronaut's point of view. In the photographs taken at mid-eclipse, the sun is completely gone, replaced by a black disk, the night side of the moon. Around it, the sky is darker than usual, but not completely empty. A faint halo of scattered sunlight glows from the edges of the window, and if the exposure is long enough, stars and even planets appear in the background. One particularly memorable image shows the full face of the moon silhouetted against the hidden sun, with a faint ghostly glow tracing one side of the lunar disk. That dim crescent is not sunlight, it is Earthshine. Earthshine is sunlight that reflects off the day side of Earth, travels across space, and gently illuminates the dark side of the moon. You can sometimes see this from Earth, when the moon is a thin crescent in our sky, and the rest of the lunar disk is faintly visible. From lunar orbit, the effect can be even clearer. In these Artemis images, Earthshine makes the eclipsed moon look like a subtle crescent, even though the sun is fully behind it. From the side that is lit by Earthshine, you can actually pick out some of the darker lunar Maria, the ancient lava plains that form the familiar patterns we see from home. One of them, Mare Crisium, appears as a dark patch in the faint glow. Just from this lighting, you can deduce where the Earth is positioned, off to the side, out of frame, shining enough reflected light to outline the moon. The duration of this eclipse from the crew's viewpoint is another surprise. On Earth, totality during a solar eclipse usually lasts only a few minutes. For these astronauts, the sun was hidden for roughly 54 minutes. The reason comes down to geometry and relative motion. On Earth, the moon's shadow is small compared to the planet, and it races across the surface as the moon orbits and the Earth rotates. An observer on the ground sits at one spot while the shadow quickly passes overhead. From a spacecraft near the moon, the situation is different. The moon occupies a large part of the sky, and as the spacecraft follows a path around it, the alignment between sun, moon, and spacecraft changes more slowly. The spacecraft can stay in the moon's shadow for much longer, stretching the eclipse into nearly an hour of darkness. Because the eclipsed moon is relatively dim, the cameras could use longer exposures. That allowed background stars to appear in the images, something that is often missing in bright, sunlit space photographs. A few planets were visible too. Saturn, Mars, and Mercury appear as bright dots off to one side of the moon in some of the frames. Neptune also lay in that part of the sky, but it is too distant and too faint to be captured in these pictures. If you look very closely at the dark part of the lunar disk in some of the images, you might notice a few bright points that do not move like stars. These are not distant suns. They are dead pixels on the camera sensors. Space outside Earth's protective magnetic field and atmosphere is filled with high-energy particles from the sun and from cosmic rays originating in the galaxy. When these particles slam into electronic detectors, they can slowly damage them, creating pixels that are stuck bright or dark. The Orion spacecraft and its cameras spent days outside the main shelter of Earth's magnetosphere, so a few radiation-damaged pixels are not surprising. Instead of being flaws, they are small signatures of the harsh environment these instruments are operating in. As the eclipse ended, the sun began to reappear from behind the moon. In the images, a brilliant wedge of light suddenly bursts from one edge of the lunar disk. This scene is similar to the so-called diamond ring effect seen during total solar eclipses on Earth. But here, the sun's reappearance also silhouettes the moon's edge in incredible detail. The boundary between light and dark along the lunar limb is not smooth. It is jagged, shaped by mountains, crater rims, and valleys. As sunlight spills past these features, the edge of the moon looks uneven, almost serrated. From these silhouettes, scientists can cross-check high-resolution maps of lunar topography that have been built up from previous missions using laser altimeters and stereo imaging. While these dramatic scenes were unfolding, the crew was busy working as observers. Some of the images show the astronauts themselves, wearing protective eclipse glasses even inside the spacecraft. The reason is simple. Being in space does not make the sun any less dangerous for human eyes. Pointing a camera or just looking out a window at the sun without protection can cause eye damage, whether you are on Earth or in lunar orbit. To capture the best possible photographs, the crew used handheld cameras, long lenses, and special setups at the windows. In one image, you can see that they covered part of a window with a dark shroud. This helps reduce reflections from inside the cabin, turning the area around the glass into a kind of improvised darkroom so that faint features outside, like Earthshine or background stars, are easier to record. Besides the eclipse, the flyby produced detailed close-ups of the lunar surface. One of the standout targets is the Orion Basin, also known as the Mare Orientale region. It is one of the youngest and best preserved large impact structures on the moon. In the photographs, Orientale appears as a set of concentric rings, like ripples frozen in rock. These rings are the remnants of a huge impact basin formed by a large asteroid or comet billions of years ago. When such an object slams into the moon at high speed, the energy released is enough to melt and to form the crust. The surface responds almost like a fluid on large scales, rebounding and collapsing to form multiple rings and central depressions. Because Orientale sits near the boundary between the moon's near side and far side, we see it foreshortened and partially from the side when viewing the moon from Earth. From the perspective of the Artemis flyby, the spacecraft could look almost directly down onto it, revealing its layered structure more clearly. Scattered across these images are countless other craters, ranging from tiny pits only a few hundred meters wide to enormous basins hundreds of kilometers across. Many of them display bright rays, narrow streaks of material that radiate outward from a crater. These rays are made of ejecta, pulverized rock hurled out during the impact and deposited across the surface. Because the rays are often brighter than the surrounding terrain, they are thought to be relatively young, geologically speaking. One notable feature visible in some of the images is Aristarchus crater. Aristarchus is one of the brightest spots on the moon as seen from Earth. It lies within a region of ancient volcanic activity and has been a target of scientific interest for decades. In the Artemis photographs, it stands out as a bright dot amid darker lava plains, emphasizing just how reflective some fresh lunar material can be. Another dark round feature, the Grimaldi crater, shows up near Orientale in some frames. Grimaldi's floor is flooded with basaltic lava, giving it a smooth, dark appearance. These lava-filled basins, or mare regions, record a period when the moon's interior was still hot enough for molten rock to reach the surface through fractures created by earlier impacts. You can also see craters like Bergius, a bright structure with extensive rays, and Vavilov, captured near the boundary between day and night on the lunar surface. When a crater lies near this terminator line, the low angle of the sunlight creates long shadows that emphasize relief. Rims look sharper, central peaks stand out, and subtle topography becomes obvious. This interplay of light and shadow is more than just visually striking. Planetary scientists deliberately seek out images taken at such lighting angles because they make it easier to estimate the heights and depths of features. Combined with data from laser ranging instruments, these photographs help refine three-dimensional models of the lunar surface. One of the most scientifically important regions imaged during the flyby is the South Pole Aitken Basin, near the lunar South Pole. This is the largest and one of the oldest impact basins on the moon. stretching over more than 2,000 kilometers. It is also one of the deepest. From orbit, the basin is not a simple circular hole, but a complex landscape of mountains, ridges, and cratered plains. Studying this region is important for understanding the moon's early history. The impact that created the South Pole Aitken Basin likely excavated material from deep in the lunar crust, perhaps even from the upper mantle. By sampling rocks from this area in future missions, scientists hope to test models of how the moon formed and differentiated. The South Polar region has another key attraction: permanent shadow. Because the moon's axis is only slightly tilted, some craters near the poles never see direct sunlight. Their interiors remain in eternal darkness, with temperatures so low that water ice delivered by comets or produced by solar wind interactions can remain stable for billions of years. Artemis-era missions aim to explore these areas directly. High-resolution images from crewed flybys help refine landing site choices and hazard maps for future landers and rovers. Another interesting aspect of the Artemis flyby is the human connection to the features being photographed. Before the closest approach, the crew suggested informal names for two small, previously unnamed craters visible near the boundary between the near side and far side of the moon. One crater they proposed to name after their Orion spacecraft, which they call Integrity. Another, located near the crater Glushko, they suggested naming in memory of a loved one. Official names for lunar features are decided by the International Astronomical Union, so these suggestions are not yet formally adopted. However, proposals like this remind us that planetary geology is not just a set of catalog numbers. These landscapes become part of human stories as soon as people start to visit, photograph, and describe them. Some of the wide-angle shots show the entire lunar disk with many of the landmarks visible at once. The bright ray craters, the dark mare plains, the ring structures of Orion tail, and other basins. One could spend a long time simply scanning these images, comparing them with lunar maps, and seeing how familiar features look from a slightly different vantage point. The flyby did not only focus on the moon. The crew also turned their cameras back toward Earth. One sequence, sometimes referred to informally as an Earthset, shows the Earth gradually sliding behind the lunar horizon. A pale blue marble with swirls of white cloud moves down toward the cratered landscape until it disappears from view. In one of these Earthset images, the sunlit part of Earth shows weather systems over the Australia and Oceania region, while the dark part of the globe is in nighttime. You can see that even at this distance, thick cloud systems are the most visible surface features. Continents are harder to distinguish without careful analysis, which gives some perspective on how dominant Earth's atmosphere is in its overall appearance. In the foreground of some of these views, a prominent lunar crater known as M crater shows terraced walls and a relatively flat interior floor with central peaks. These central peaks form in larger, so-called complex craters. When the impact happens, the surface is briefly fluid on a large scale. After the initial excavation, the floor rebounds upward and then collapses, leaving a peak in the middle and terraces along the slopes. Observing these structures from oblique angles helps scientists understand the energies and mechanical properties involved in impact cratering. There are also modern echoes of famous historical images. The Apollo 8 mission in the late 1960s captured an iconic photograph of Earth rising above the lunar horizon, sometimes called Earthrise. Later missions, such as Apollo 17, added their own full-disk Earth portraits. The new Artemis images show similar scenes, but with different lighting, different cloud patterns, and modern camera technology. In one photograph taken just as the spacecraft emerged from behind the moon after a communication blackout, the thin crescent Earth rises above a rugged lunar foreground. The Earth looks far smaller than in many older images, because the spacecraft is farther away from home than the Apollo capsules ever traveled. These crescent Earth images have another interesting twist. From Earth, we are used to seeing the moon as a crescent, while Earth is mostly full in the lunar sky. Here, the roles are reversed. Because the spacecraft is near the moon and looking back, the Earth appears as a crescent, partially lit by the sun, while the moon below is more fully illuminated. The phase you see depends entirely on your vantage point in the Sun-Earth-Moon system. The crew also took images showing the line between day and night on Earth, the so-called terminator, slicing across the globe. From space, this boundary is sharp at small scales, but gently curved at the planetary scale. Along the terminator, you can see long shadows in cloud systems, and a gradual fading of brightness, just as we experience at dawn and dusk. Capturing all of these views required careful planning. During the close lunar approach, the crew had roughly a 7-hour window to conduct observations. Within that time, they needed to perform navigation tasks, monitor spacecraft systems, and also operate cameras and scientific instruments. The eclipse itself lasted nearly an hour, and additional time was spent imaging the surface, the Earth, and the surrounding star field. At one point during the flyby, the spacecraft passed behind the Moon, as seen from Earth. When that happens, radio signals between the spacecraft and Earth cannot travel straight through the lunar body. For about 40 minutes, there is a planned communication blackout. No voice, telemetry, or video can reach Earth. This is not a malfunction. It is a simple consequence of radio waves being blocked by solid rock. Mission controllers know exactly when this will start and end, because the spacecraft's trajectory is precisely calculated. For the crew, it is a period of relative quiet. They can continue their observations and tasks autonomously, knowing that contact will resume once they reappear from behind the Moon. Interestingly, this radio shadow is one reason why the far side of the Moon is considered a promising location for future radio astronomy. The Moon blocks radio noise from Earth, creating a relatively quiet environment for listening to faint cosmic signals that are otherwise drowned out by human transmissions and atmospheric interference. The sheer number of images and videos captured during this mission raises another practical consideration: data transmission. The spacecraft communicates with Earth through the Deep Space Network, a global system of large radio antennas. These antennas are shared among many missions exploring the solar system. Bandwidth is limited, and priority always goes to essential data such as spacecraft health, navigation, and critical scientific measurements. High-resolution photographs and video files are large compared to simple telemetry. It is not possible to stream every frame back to Earth in real time. Instead, the data is stored on board in digital memory. Over time, when communication windows allow and bandwidth is available, batches of images are transmitted back, often compressed and scheduled carefully. When the spacecraft returns to Earth, additional data can be retrieved directly, allowing the full resolution versions to be preserved. Beyond their aesthetic value, these images have clear scientific uses. Repeated imaging of the same areas under different lighting conditions helps refine measurements of surface reflectivity and texture. Comparing new photos with high-resolution maps from previous orbiters allows scientists to look for subtle changes, like fresh small craters that may have formed from recent impacts. This contributes to our understanding of the current impact rate in the Earth-Moon system. The detailed views of certain craters and basins can be combined with spectral data from other missions, which measure how the surface reflects different wavelengths of light. This helps identify rock types, from iron-rich basalts in the Maria to anorthosite in the highlands. When planning landing sites for future crews or robotic missions, knowing which areas expose deep crustal rocks, volcanic materials, or possible ice deposits is crucial. These human-taken photographs also provide something that automated instruments often lack: flexible, opportunistic framing. A person at a window can quickly adjust composition, zoom in on a feature that looks interesting, or capture a serendipitous alignment of Earth and Moon in a single frame. While orbiters with scanning cameras produce far more uniform coverage and data volume, there is still real scientific and educational value in images taken by astronauts who can react in real time to what they see. The mission also reminds us how much can still be learned from a place as familiar as the Moon. For decades, it has been mapped, imaged, and measured by robotic spacecraft. Yet new viewpoints and trajectories still reveal subtle details. The precise look of an almost hour-long eclipse from lunar orbit, the way Earthshine outlines the dark side of the Moon in color photographs, the jagged silhouette of the lunar limb against a returning sun, and the sight of a crescent Earth sinking behind a cratered horizon. Looking ahead, Artemis missions aim to go beyond flybys. Future steps include inserting spacecraft into stable lunar orbits, constructing the Gateway Station as a staging point, and eventually landing crews near the Moon's south pole. There, astronauts will directly investigate ice in permanently shadowed regions, collect rock samples from ancient basins, and deploy instruments to probe the Moon's interior and environment. There are many open questions that make the Moon scientifically compelling. The exact distribution and accessibility of ice at the poles is still being refined. The detailed timeline of the early bombardment of the inner solar system, recorded in the ages of lunar basins, is not yet fully pinned down. The thickness and composition of the lunar crust and mantle, especially at great depth, are inferred from models that could be tested with new samples and seismic measurements. The Artemis program, including this flyby, is part of a broader effort to turn the moon into a natural laboratory for answering these questions. High-quality imagery is one small but important piece of that work. It guides where we go next, helps calibrate models, and offers ground truth for data collected by remote sensors. Meanwhile, for everyone back on Earth, these photographs provide a clear, fact-rich glimpse into our place in space. They show a moon that is not just a bright disk in the night sky, but a complex world with mountains, basins, and a long geological history. They show an Earth that is vibrant yet small, only one world among many visible in a single frame. And they show that even familiar objects, when seen from a new angle with modern instruments, can still reveal new details and inspire new questions.